moving on to 16.2, 16.3. I'm kind of doing this together all at once. 16.3 is fundamental theorem of line integrals, but I'm not following it precisely. So going over a number of definitions and theorems now. This is a little tedious, like more tedious, but we need to get through it first. So let's take a look. So we just did the example, which is kind of like the homework example, what you would do on finding a potential function. And so make sure you know how to do that. Let's go on to independence of path concept and fundamental theorem of line integrals. We won't spend like a lot of time on it, just need you to be aware of it, really. So let's take a look. So first thing is independence of path and that concept. So let me show you that. Excuse me. So the idea is for independence of path, and I'm going to show you this first, and then we'll go back and define it, is suppose you have a region R in the XY plane, something like that, and it ends up, the definition, it'll be open, so I drew it open. And you are going from point A to point B. And so the idea is that it doesn't matter the path you take to get from A to B. We'll call that C1. That, and we'll do another one like that. Essentially, the integral, which might be like work or something, if you have a vector field, so you got to picture like a vector field coming through this. And I'm just going to draw just an idea. So that's your vector field F. So this always pertains to vector fields. And when you think vector field, you have to have something in mind. I like to have in mind usually gravity or magnetism or like electrical fields. If you haven't worked with that stuff before, then I would just think gravity. Basically, it's pushing down, like everything is going down. So the idea is it doesn't matter the path you take, you get the same integral. So roughly, this is just shorthand stuff. You take the integral of whatever of C1, it's the same as integral C2. There's my region R. And so if you subtract those, C1 minus C2, you get 0. But if you consider it as a closed path, and you start at A and you go up, and then you come back like that, or vice versa, you go up and you come back to the same point, then that integral, let's come back up here, save space. We call that around a closed path. So if there's a little circle there, it means it's a closed curve around, and that is equal to 0. Okay, so that's the concept of independence of path. So now let's get a little more careful and define them. So here's a few definitions. So a region R in 2D or 3D is connected. We're defining connected first, sorry. If any two points in R can be joined by a piecewise smooth curve lying entirely within R. Can be joined by a piecewise smooth, so it can be, bouncy and stuff. Piecewise smooth curve lying entirely within R. And I'm not going to draw this open this time. So you have some, so this is very simple description. So like take that one, for example, and then you take these two regions. So this region, like one's connected and one's clearly not connected. I mean, it's not a big deal, but that's how we end up defining stuff later. So you have any 2 points, arbitrary points in the region, A to B, and then say A to B. So those are any arbitrary points in the region. It can be connected by a piecewise smooth line. Sometimes I've seen this defined with line segments. It's like individual line segments. And of course this one, so it could be a curve, Obviously the one on the right, these points are outside the region. So if this is my region R. This is clearly not connected, so those are points outside R. Okay, so our region is going to need to be connected. Yeah, it makes sense. Next is the definition of independence of path. Well, let's try to fit it here. I don't know if it'll work. All right, so definition, and the description was above. This is the actual definition. Definition of independence of path. Let R be an open connected region. Let R be an open connected region. And it could be a solid. Like I'm doing this really in terms of the region because we're going to be integrating over regions and then up to a surface kind of thing. But it could be actually a solid. Okay, open connected region. We'll just call it R. Let C1 and C2 be any. Well, I'm not going to say it. They're arbitrary by the way I'm defining it, so I'm going to leave that statement out. Let C1 and C2 be piecewise smooth curves lying entirely within R. And by not describing what they are, they're obviously arbitrary. Implied to be arbitrary. So let C1 and C2 be piecewise smooth curves lying entirely within R. Then the integral over C of f dot dr is independent of path if integral over C1 of f dot dr is equal to the integral over C2 of f dot dr. So it's taking two arbitrary different paths in R, and I'm leaving off a few details, I can tell, but you get the same integral. So, but let me draw the picture because that's really what I want you to pick. I want you to visualize. So you have a open connected region. Okay, so that's open and connected. And we're going from A to B. I've probably left off a few of these little details. And you have two paths. So this is my open and connected region R. You're going A to B. So you could have a path like this. There's your C1. Your C2 is another path like that. Let's change the color just for fun. You have another path like that. That's your C2. And if so basically it's what it's saying, as you integrate from A to B, it doesn't matter what path you take, you're going to get the same result. So you got to think of it as if you're considering like gravity, then if you're going from here to here, it doesn't matter the path you take. It's like you're pushing against gravity the same amount, ignoring air resistance and stuff like that, because wind and air resistance will mess things up. Okay, let us continue. Again, just a lot of definitions. Next is the theorem. This connects independent of path and conservative vector fields. This is really important, especially for your future work. Okay, I'm going to start highlighting some of these things, see if they stand out a little bit. There's that theorem. Here's the definition of independence of path. Definition of, what was this, connected? Independence of path. Okay. This next theorem is pretty cool. All right, so this says that the integral, and I'm leaving off a lot of definitions, a lot of details just because to speed things up. When I get to the theorems you're going to really be applying, then I will tighten it up a little bit. So integral, there's line integral over C of f dot dr is independent of path if and only if f is conservative. So that's the major idea. If you are in a conservative vector field, it doesn't matter how you get from point A to point B. You can integrate. The path can be like that. It could go straight there. It's like you got to visualize it taking, or mentally thinking, taking the same work from lifting something from here to here. Whether you lift it straight up or across and up, it's the same work. Again, ignoring air resistance. Okay, next one is along these same lines. I'm going to move this up just a little bit. So next theorem. This is a closed path. So I simplified this a little bit. So you take any closed path. If you integrate around a closed path, then it is zero. The work basically is zero. So you integrate around a closed path. That's what that circle will mean, is closed. So f dot dr is 0, then f is conservative. Excuse me. So if that's true for any c, so f must be conservative. Well, if it is conservative, then it's always 0. So f conservative. C is closed. And it's in an open connected region and all that. I'm just trying to beat it up a little bit. So closed curve. So closed curve. Okay. So this next theorem summarizes everything. So let f have continuous first partials in an open connected region R. Let C be a piecewise smooth curve in R. Then T, F, A, E. Probably not seen that before. That means the following are all equivalent. So these are all equivalent statements. 1, F is conservative. That is, there exists a little f such that the gradient of f is equal to capital F. 2, the integral over c of f dot dr is independent of path. 3, the closed curve of f dot dr must equal 0 for all C in R. So for every closed curve in R. And so that basically leads us to the fundamental theorem of line integrals. The fundamental theorem of line integrals: let C be piecewise smooth curve in an open connected region R. We can have C be defined by R of t, so x of ti plus y of tj plus z of tk for t in the closed interval from A to B. And then we want a vector field. So we're going to let F be conservative, a conservative vector field. And then we get this theorem, and this is really a direct result of, or equivalent to, the fundamental theorem of calculus. So we have the integral of f dot dr over c is equal to the integral of the gradient of f dot dr, because remember, if it's conservative, then that little f exists. And so if you do that, you basically just evaluate at the endpoints. So you get, those are like partials f, well, you just evaluate. And so this is equal to f of x of b. Well, this is over c. And so it's just going to be b minus a. X of b, y of b, z of b, minus f x of a, y of a, z of a. Okay, so that's basically it. You evaluated the endpoints. So one of the concepts really, like if it was just x, so the fundamental theorem of calculus, so let me just show you this. If fundamental theorem of calculus says basically if you go a to b of f dx, and f is the antiderivative of f, then that's the integral from a to b of df dx. And so you just evaluate at the endpoints, f of b minus f of a. So that's what that would mean. So this is equivalent to the fundamental theorem of calculus. Okay, and let's just do one example. It's not real heavy on this topic, more of the finding potential function and vector fields and that sort of stuff. Okay, but this is just one simple example. So if we integrate from 0 to 1 pi halves of e to the x sine y dx plus e to the x cosine y dy, then our f is e to the x sine yi plus e to the x cosine y j. So it would be like in 2 dimensions. So first of all, is that conservative? And it is, because this is just 2D. So if you look at the partial, so this is m, this is n. So partial n with respect to x would just be e to the x cosine y. And then is that equal to the partial m with respect to y? Well, the partial of sine is cosine. So you'd get e to the x cosine y. So that's true. So therefore, f is conservative. And so that is going to be your potential function, is just e to the x cosine y. Oh, I'm sorry, e to the x sine y. So you get, this is equal to e to the x sine y, and then you evaluate that from 0 to 1 pi. One pi halves. So that's just e sine of pi halves is 1 minus 0, so that's just e. So you basically just would find the potential function and then evaluate at that point. Let's see, I guess I could show you that. I mean, you have f of x y equal to e to the x sine y, and you can see that m is partial f with respect to x, which is e to the x sine y. That's the same. That's just unique because of the x, really. And then n is partial f with respect to y, which is e to the x cosine y. So those are your two partials that would go for your function here, and then that makes sense. Okay, so that's how you would apply the fundamental theorem of line integrals. And again, we don't focus real heavily on that. So after this is basically 16.1, 16.2, 16.3. We go on to Green's theorem, and we hit these basically major theorems. And then surface integrals as well. That's the other thing we hit too.